feel free to ask any questions that they might have in the Q&A. They'll find that button at the bottom of their Zoom window. We'll curate the questions and try our best to answer all the questions either during the talk or at the end of it.
Sounds good.
Great. So otherwise, I'm extremely happy to that we have Mary Wootters today. Mary is an assistant professor of computer science and EE at Stanford. She got her PhD in math from the University of Michigan, and then she was a postdoc, an NSF postdoc at Carnegie Mellon. She's won an NSF Career Award, a Sloan Research Fellowship, and does really interesting work in theoretical computer science, applied math. She's done work on error correcting codes, randomized algorithms, and related area. And today she will tell us about sparse recovery for orthogonal polynomial transforms. So floor is yours, Mary.
Thanks. Yeah, so thanks for the invitation, and thanks, Ryan, for the introduction. Yeah, so I'm Mary Wootters from Stanford, and I'm going to talk about sparse recovery for orthogonal polynomial transforms. And this is joint work with Anna Gilbert at Yale, Albert Gu at Stanford, Chris Ray also at Stanford, and Autry Rudra at Buffalo. And like Ryan was saying earlier, please do ask questions. And I guess there's a Q&A box that you can type them in. They're very appreciated. Cool. Okay, so let's get started. So this talk is about, as you might guess from the title, sparse recovery for orthogonal polynomial transforms. So I'm going to define these words a bit more precisely, or define them at all in a moment, but for those of you who already know what they mean, that the punchline is going to be sublinear-time sparse recovery algorithms for orthogonal polynomial transforms, in particular for Jacobi transforms, discrete Jacobi transforms. Okay, but before I define what these objects are, let me talk about some motivation for this coming from the sparse fast Fourier transform. So the discrete Fourier transform you're probably familiar with is a matrix here. Can y'all see my mouse?
Yes.
Yes. Great. Thanks, Mark. Actually, can I turn it into a pointer? Is that a thing? Oh, I can. Aha, there we go. Now I have a pointer. Yeah, so the discrete Fourier transform matrix F is just a matrix where the ijth entry is omega to the ij, where omega is nth root of unity. And the sparse fast Fourier transform problem is as follows. So suppose I have some vector x of length n, and let x hat be the transform f times x. And suppose that x hat is sparse or nearly sparse. So that means that here's x hat over here. It has only k big entries, and the rest are really little, for some k which is much less than n. And the problem is, given query access to x, our goal is to find x hat as quickly as possible. So there's been a lot of work on this, going all the way back to the original fast Fourier transform. So obviously, due to the fast Fourier transform, we can find x hat regardless of whether or not it's sparse in time big O of n log n. But there's been a lot of really exciting work over the past couple of decades showing that if x hat happens to be sparse, then in fact you can find it much, much faster in time closer to k log n than n log n, where k is the sparsity. So if k is much less than n, this is big savings. Right. So this is really cool. So the problem that we're trying to solve in this work is sort of building on the sparse Fourier transform, is to say, well, what about general orthogonal polynomial transformations? So that means instead of looking at the discrete Fourier transform f, we're going to replace Fourier with a bunch of other names you may have heard of, like Chebyshev or Legendre or Geigenbauer or Jacobi. So all sorts of orthogonal polynomial transforms which are used all over the place in math, physics, computer science, and so on. And just like the fast Fourier transform, there are fast versions of all of these transforms. That is, if I don't care about sparsity, I can compute f times x in nearly linear time. And so then it makes sense to ask the same question. Well, what happens if I do know that x hat is sparse or nearly sparse? How quickly can we find it given query access to x? And that's the question that we're going to be asking in this talk today. So the outline for this talk is the following. First, I'm going to tell you what orthogonal polynomial transforms are. Then I'm going to talk a little bit about the sparse recovery problem for OP transforms and related work. And then I'll tell you our main results, which is a sublinear-time sparse recovery algorithm for Jacobi transforms under some assumptions. And then the rest of the talk, sort of after that, will be explaining how we get these results. So I'll give a real quick overview of the sparse FFT, which is sort of the basis that we're building on to get these algorithms, and then a few more details about our algorithm and the problems that arise when trying to generalize the FFT. Okay, so that's the plan. So let's get started with orthogonal polynomial transforms. So first, what are orthogonal polynomials? So orthogonal polynomial family is a bunch of polynomials, P0, P1, P2, ... So that the nth polynomial Pn has degree n, and so that there are weights W of x, so that the polynomial family is orthogonal with respect to these weights. So that is, for any I and j, if I integrate Pi against Pj with respect to the weights W, I'm going to get 1 if I is equal to j and 0 otherwise. And for this talk, I'm going to assume that the orthogonality is defined over some finite interval. And if it's defined over a finite interval, then without loss of generality, that interval may as well be -1 to 1. This does exclude some orthogonal polynomial families, like Hermite or Legendre polynomials, where the orthogonality is defined over an infinite interval. So our results are not going to apply to those. And it's an interesting open problem to try to extend this. But even with this restriction, orthogonal polynomials defined on finite intervals are a really rich class. So some examples you might have heard of include Chebyshev polynomials. So they look like this. They come in a couple of flavors. And Chebyshev polynomials show up all over the place in numerical analysis, approximation theory, differential equations, and so on. Another example are Legendre polynomials. These are useful in mathematical physics, also in differential equations. They've recently shown up in recurrent neural networks, so very, very common family. There's also you might have heard of the Geigenbauer polynomials. So these are a broader family of polynomials indexed by some parameter alpha. They generalize both Chebyshev and Legendre polynomials. So by picking alpha appropriately, you can recover either of those others. And even more generally, there are the Jacobi polynomials, which is what we're mostly going to be focused on in this talk. So this is a very general family of orthogonal polynomials, or collection of families of orthogonal polynomials. They're indexed by two parameters, alpha and beta. And by choosing alpha and beta appropriately, you can recover the Geigenbauer polynomials, Legendre, Chebyshev, and a whole bunch of other things besides. So this is a very general collection of orthogonal polynomials. And this is the Jacobi polynomials are mostly what we're going to be focused on in this talk. So we don't need to know too much about orthogonal polynomials to actually do this talk, but the one thing that we do need is Gaussian quadrature. So what is this? So suppose that P0, P1, P2, and so on are an orthogonal polynomial family. And suppose that the roots of some Pn, capital N, are lambda naught, lambda 1, up to lambda n minus 1. So for example, in this picture here are the 5 roots of, I guess, the 5th Legendre polynomial. So here's a fact. All of these roots are distinct, and they all lie in the interval -1 to 1. And another fact, this is called Gaussian quadrature. For any orthogonal polynomial family, P1, P2, P3, and so on, there exist weights WL, so that for any polynomial g of x of degree at most 2n minus 1, if you integrate that polynomial g sort of against the weight function w that comes with the orthogonal polynomial family, sort of the weights with which that family is orthogonal with respect to, then this integral is in fact exactly equal for low degree polynomials to just a sum of those polynomials on evaluated at the specific roots of P sub n, weighted appropriately by the weights wj. So Gaussian quadrature is useful all over math and engineering, especially in numerical analysis. And for us, it's useful because it tells us how to turn a continuous family of orthogonal polynomials into a discrete orthogonal transform. So that's what I'm going to talk about next, discrete orthogonal polynomial transforms. And for the rest of this talk, I'm just going to drop the adjective discrete. When I say orthogonal polynomial transform, I mean the orthogonal matrix that I am about to describe. Okay, so let's let lambda naught through lambda n minus 1 be those roots of Pn that we just talked about. And I'm going to define two matrices, P sub n and F sub n, as follows. I know that P sub n is overloaded. This one's bold and it's going to go away soon, so sorry about that. So the bold P sub n is equal to this matrix. So the rows are indexed by the evaluation points lambda naught through lambda n, and the columns are indexed by the orthogonal polynomials P naught through Pn. And the thing that goes in the j-ith position is the ith polynomial evaluated at the jth evaluation point, lambda j. So this is the matrix P sub n. We're going to be interested in a sort of renormalization of it, the matrix F sub n. And this is just when I take P sub n and I'm going to normalize it by multiplying the rows by the square roots of these weights. And the reason to do this, to normalize it in this way, is because when I do this, I get an orthogonal matrix. So F sub n is orthogonal. We can quickly check this just by computing F sub n transpose times F sub n. Okay, so what is this? If we draw out the boxes and just sort of stare at it, we get that F sub n transpose times F sub n is equal to Pn transpose times this diagonal matrix with the weights on it times P sub n. And if you do it out, you get some matrix where the ijth entry is indexed by the ith polynomial pi and the jth polynomial pj. And the value here, just sort of doing out the sum, this is equal to the sum over L of pi lambda L, pj lambda L times the weight WL, which by that convenient Gaussian quadrature thing that I just said is equal to the integral from -1 to 1 of that same thing where I replace the discrete weights WL with the weight function WX. And then by orthogonality, this is just equal to 1 or 0, depending on whether or not I is equal to j. So what that means is that this whole matrix here is the identity, and indeed F sub n is orthogonal. Hooray. Okay, so these are the orthogonal matrices that we're going to be interested in for this talk. And these orthogonal matrices, that is this particular choice of evaluation points, the lambda i's, show up a bunch. So one example, I guess, is the discrete Fourier transform that we talked about at the beginning. So here the relevant polynomials are just the monomials x to the L. The evaluation points are omega to the j. So these are the nth roots of unity. And then we just evaluate x to the L at omega to the j to get the entry omega to the jl. Okay, so actually the finite Fourier or the discrete Fourier transform does not fall into what we're talking about, because we're talking about things that are orthogonal on sort of the interval -1 to 1 rather than on the circle in the complex plane, but similar in spirit. Another example which does fall into what we're talking about is the discrete cosine transform. This is what happens when you do the transform or when you do the construction that I just said with Chebyshev polynomials of the first kind. Discrete cosine transforms are used all over the place for image compression, audio, video, stuff like that. There's also, you might have heard of the discrete de Legendre transform, the uniform Jacobi transform. These are what you get when you take the relevant orthogonal polynomial family and form this matrix. So these matrices are studied all over the place. And as I mentioned before, all discrete OP transforms have fast algorithms. So just like the FFT for the discrete Fourier transform, there are near linear time algorithms to do matrix vector multiplication for these matrices. And this has been known for a while. And so the main question that motivates this work is, do they also have fast sparse algorithms like the sparse FFT that I talked about just before? Cool. So that's going to lead us to the next section of the talk about sparse recovery for OP transforms. What is the problem and what's known? I guess before I moved on, I just blew through a bunch of jargon. Are there any quick questions at this point? Just type into the chat box.
So far, nothing that we couldn't handle.
Okay, thanks, Mark. Cool. Okay, so the question that we're after then is, sparse recovery for OP transform. So what is this problem? So here's the goal, or sort of a cartoon version of the goal. I'll give a more precise version with some quantifiers and so on in a moment. The goal is this. So we have our matrix F sub n, which now it's an orthogonal polynomial transform. And we have query access to some vector v. We know that f times v, which I'll call v hat, is k-sparse. And so what that's going to mean for this talk is that I'm going to be able to write v hat as x hat plus w hat, where x hat is k-sparse, so this is sort of like the sparse part, and w hat is some noise, so it's going to be some vector with small L2 norm. And our goal is going to be to find some z hat, which is an approximation to v hat. Z hat's going to be k-sparse, so that v hat minus z hat is small, and we want to be able to find this z hat in sublinear time in n, using queries to v. All right, so that's the goal. So there's been some work on this problem for general orthogonal polynomial families, although not nearly as much work as there has been for the Fourier transform. So one body of work addresses the sample complexity of this problem. So if I don't care about the sublinear, or if I don't care about a sublinear time algorithm, I don't care about how long it actually takes me to recover this z hat, I only care about how many queries I make to v, then we actually understand the sample complexity quite well. And this is coming out of work from compressed sensing. So just looking at this little picture here, another way to write our problem is if I multiply both sides by f transpose, both sides of the equation from the previous slide by f transpose, what I get is a picture that looks like this. I have f transpose times some sparse vector equals some vector that I have query access to. And my goal is to use as few queries as possible over here, which basically means I want to find, a couple of rows, as few rows as possible of f transpose, so that given this sort of short fat matrix phi times this sparse vector, I can recover the sparse vector. And this is exactly the compressed sensing problem. And there's been quite a bit of work to show that if f is reasonably nice, in particular if it's an orthogonal matrix with entries that are not too big, then if I sample just random rows, then approximately k log n, more or less rows, maybe a little bit more than that, are enough to solve this problem. So there's been a lot of work showing that for this particular case, the sample complexity of k polylog n is roughly correct. Similarly, also in the context of compressed sensing, there's been work showing that even if the matrix, even if we don't choose these evaluation points, lambda I to be the roots of the nth polynomial, this might also work, or this can also work if we choose them cleverly. So all of this work kind of pins down the sample complexity, but it doesn't really say anything about sublinear time algorithms. The algorithms that come with these things generally take time polynomial in n, whereas we're looking for something polynomial in k. There's also been some existing work on sublinear time algorithms for Chebyshev and Legendre polynomials, including work by Mark, who's here. Yeah, so this work by Hu, Iwan, and Kim from 2017 handles the case of Chebyshev polynomials and Legendre polynomials. So both of these sort of essentially go by a reduction to the SFFT, although for Legendre it's a little bit more complicated. One difference between these works and our work is that they work in the continuous setting and we're working in a discrete setting. There's also been some work on sparse OP transforms for more general OP families based on Prony's method. So Prony's method can recover an exactly k-sparse, I'm sorry, I wrote polynomials there, but can recover k-sparse vectors with big O of k queries, which is really cool. But at least as far as I know, there are no theoretical results along these lines about robustness to noise, except for the Fourier transform and very closely related families. And so our goal in our work is to get theoretical results, even with a little bit of noise. Cool. OK, so that's sort of a quick overview of what's been done. And the takeaway, hopefully, is that there's been tons and tons of work on the Fourier transform and on sample complexity, and not so much work on sparse orthogonal polynomial transform for general OPs, for more general families than Chebyshev or Legendre. So that's sort of the area that we're hoping to tackle with this work. So what are our results? So I'm first going to sort of list our contributions kind of at a high level, and then I will sort of go through and state slightly more formal theorem statements. So the main contributions, there are 3 of them. So the first is like I said at the beginning, sublinear-time algorithms. So actually the first, as far as we know, sublinear-time algorithms with provable guarantees for approximately sparse recovery for discrete Jacobi transforms. So like I mentioned before, Jacobi polynomials are a really general class of orthogonal polynomials. They capture Chebyshev, Legendre, Geigenbauer, Zernike, lots of other polynomials, orthogonal polynomial families. So this is a very general class. Our algorithms run in sublinear time, so time polynomial in k-log n. But unfortunately, it's subject to some assumptions. So we need to make a few assumptions on the vector v that we're trying to recover. So in particular, we're assuming that v hat has sparsity that's reasonably spread out in a way that I will quantify in a moment, and also that the noise w is not too large. The way we establish this result, the way we get these sublinear time algorithms, is in 2 steps, and these are our other 2 contributions. So the first is a black box reduction to the one-sparse case for general orthogonal polynomial families, or reasonably general orthogonal polynomial families, not just for Jacobis. So that is, we show that if you have an algorithm that can solve the one-sparse case for your favorite orthogonal polynomial family, this gives rise to an algorithm to solve the k-sparse case. And then the next piece to sort of finish it off is a solution to the one-sparse case for Jacobi polynomials. And then we can take these 2 black boxes and kind of stick them together and get the first thing again. Okay, so instead, before I go on and state a little more precisely what these things mean, let me just discuss a little bit some strengths and weaknesses of these results. So there are some things about these results that I'm happy about. Yeah, go ahead.
One question based on something that someone asked in the chat. I believe that some of the work involving Prony methods uses samples from the derivative of the functions as well. Do you use samples from the derivative of the function yourself? And if you don't, do you think that might help?
It's a good question. We don't. I have not thought about whether or not that would help. And
okay, yeah.
Yeah, it's a nice idea. I will think about it. Thank you for the suggestion.
No, it's okay.
Yeah, the answer is we do not use samples from the derivative.
That's the most important thing. I thought you might want to clarify.
Yeah. Yeah. So basically, like I said in the setup, we're only going to be sampling this vector v. So that's all we have is query access to v. Great. Okay. Yeah. So again, before I go on to state these results a little bit more formally, yeah, there's some discussion. So there's some things about this that make me happy. So first, you know, it's, as far as I know, that there are no other algorithms that do this, so that's cool. The Jacobi class of OPs is very, very general, and our algorithms run in sort of solidly sublinear time. This k-log n is looking very nice. On the other hand, there are some downsides to this result. So first, there's this polynomial in front of the k-log n. So as I said, with the sparse FFT, those algorithms eventually, you know, after a long line of work, can get down to time basically k-log n, or at least k polylog n, in particular linear in k. So this polynomial is not so great. And also these assumptions are somewhat restrictive. Ideally, we would not have these assumptions. So as I talk about the results and our proofs of them, I will explain where these assumptions come up and hopefully ways that we might be able to remove them in future work. Another positive thing is that this sort of black box reduction to the one sparse case works for general orthogonal polynomial families subject to a few restrictions. So yeah, if you have your favorite orthogonal polynomial family, just come up with a one sparse solver for it and it'll work. Okay, so those are the results. Let me say them in a little bit more detail now. So what I'm going to do now is just sort of do sort of three theorem statements in a row, and then I'll talk about the proofs. So the first statement, so this is the sublinear-time algorithm for Jacobi polynomials. So suppose that P sub n, alpha beta, are the Jacobi polynomials, and suppose that Fn is this orthogonal matrix that we talked about before. So here's Fn, it looks like this, just as a reminder. And suppose we have some vector v, which is x plus w, so that the Jacobi transform of v hat looks like this. So v hat is equal to x hat plus w hat, and x hat is the spiky part, and w hat is the noise. And this is going to be subject to some assumptions. So the assumptions are that x hat is going to be k 1 over k sparsely separated. And what I mean by that is, well, first off, it's k sparse. So there's only k non-zeros in x hat. And secondly, that the support of the sparsity is reasonably spread out, meaning that there are no two of these spikes have indices that are closer than roughly n over k squared. C here is just some constant from each other. So that's assumption 1. Assumption 2, oh yes, also note that this does hold, for example, for a completely random support with high probability. So this will work for like a random vector. But it is an assumption on top of worst case. Assumption 2 is that the noise w hat is fairly small. So in particular, if let's say that the smallest spike here, this one, has magnitude, let's say a, our assumption is that the L2 norm of w hat is significantly less than a, less than delta times a. So that's our other assumption, is that the noise is pretty small. So these two assumptions are the drawbacks, and hopefully we can find a way to lift them in future work. Cool. Okay, but the modulo of these assumptions, the conclusion, which makes us happy, is that with probability at least 0.99, our algorithm is going to recover some z hat, so that x hat minus z hat is small in L2 norm, that the L2 norm is no more than delta times the L2 norm of x hat. And the running time and query complexity of our algorithm is polynomial in k log n divided by delta. Okay, so this is the statement for the sublinear-time algorithm for Jacobi polynomials. And like I said, there are sort of two steps to getting this. The first is a black box reduction to the one-sparse case. So if you have a one-sparse solver, this gives you a k-sparse solver. So here's what this theorem looks like. So suppose that y'all can see my slides, yes?
Yes.
Okay, thanks. Zoom just gave me a message that was like, caused me to believe that something might be wrong. Okay, glad. You can see my slides and not the presenter view, right?
Yep.
Okay, cool. Sorry. Right, yeah, so here's the theorem for the reduction from the one-sparse case to the k-sparse case. So suppose that P1 through Pn is an orthogonal polynomial family with reasonably spread out roots. So this is a mild assumption which does hold for polynomials. Then if Fn is this orthogonal matrix that we had before, let's assume also that it doesn't have any entries that are too large. So for example, let's suppose that each of its entries are on the order of 1 over square root n. Again, this does hold for Jacobi polynomials. Then the conclusion is that if you have an algorithm that solves this problem, so here's sort of the one-sparse problem. So I have x hat just consists of a single spike of height a, and I have some noise, which is not too big. So in L2 norm, it's no bigger than delta times a, or order of delta times a. And let's suppose I have a algorithm that makes q queries to the inverse transform of this spiky vector, and it runs in time t. Then it's going to return, and it returns an algorithm. Sorry, it returns a one-sparse vector, a twiddle times eh, so that h is the correct h, and a twiddle is close to a, with high probability. If I have such a one-sparse solver, then in a black box way, I can turn this into a k-sparse solver, which works on vectors that look like this. So this is subject to the assumptions that I had on the previous slide, except now there's a parameter gamma for how far apart these things have to be. And the cost is basically just a blow up of polynomial in k divided by delta gamma on the query time and the running time. And then it's going to return some z hat, which is close to x hat with high probability. So that's the statement. Okay, so then now that we have this reduction, the last piece of the puzzle is to actually have a one-sparse recovery algorithm for Jacobi polynomials, or for Jacobi transforms. And so here's that theorem statement. So once again, consider the matrix Fn arising from the Jacobi polynomials P sub n alpha beta for any alpha beta bigger than -1. And suppose you have a one-sparse situation, again, that looks like this. Then the conclusion is that there exists an algorithm that makes some number of queries, where that number of queries is logarithmic in n and polynomial in 1 over epsilon. Epsilon here is the requirement on the noise, and also runs in about that same time. And it's going to return the thing we wanted it to return, so the correct value for h, and also an estimate a twiddle for a that is pretty close. So those are the theorems. And like I said, the second and third theorems imply the first. So if I have this reduction from one-sparse to k-sparse, and I have a one-sparse solver, then I can put these two things together, and I'm going to get my sublinear-time algorithm for discrete Jacobi transforms. Okay, so for the rest of the talk, I want to focus on how we actually do this, and the basic ideas that we're going to use are in fact mostly present in existing algorithms for the sparse Fourier transform, sparse fast Fourier transform. So I'm going to start by giving an overview of how that works. Before I move on, any questions at this point that showed up in the chat?
Just a quick one, Mary. What do you have, like a handle on the power in the polynomial and the polylog and the error estimates?
Yeah, so great question. Yes, the question is what's the power in the polynomials? So the power on k is 8. Yeah, so it's however, I guess we'll sort of see as we go through the algorithm. Basically, I don't know how to get it less than 2 or 3, and at the point that we realized that we couldn't get it less than 2 or 3, we kind of didn't focus too much on getting it small, so we didn't pay too much attention to the power. So certainly the 8 can be improved, but I think it's a really interesting question to get it down past 2 or 3, and I'll try to point out some of those bottlenecks when they come up.
Or on delta?
On delta, I want to say it's 5/3. Wait, hang on, I have a hidden slide just for this. Can you see my hidden slide with all my tiny text?
Yes, we can.
Okay. Oh, shoot, but there's still a polynomial in it. Yeah, so here's this 5/2, and this polynomial, certainly less than 8, but still not, same situation as with the k. We didn't try too much to optimize the power of the poly.
Thanks.
Yeah, really good question.
One more thing that someone asked about, Mary, I guess. They wanted to know how sparse the z is that you're outputting. Is it exactly k-sparse or maybe a little bigger?
It's exactly k-sparse.
Okay, so then I was putting things slightly wrong into the chat. I said it might be bigger than k-sparse by a bit. So it is exactly k-sparse. That's good. Then there are other questions about the assumption about being spread out. And I just wanted to sort of verify, you're always talking about the discrete sort of transform. So spread out just means the entry in the transform vector.
Exactly. Yeah, so I'm talking about the discrete transform. So by spread out, I mean that the spikes, if this spike happens at the evaluation point, which is the root lambda I, and this one happens at lambda j, then I minus j should not be too close together. Exactly.
Yep. Okay, great. Thanks.
We do also make an assumption that the roots themselves are somewhat spread out. So that's maybe a more continuous notion. That assumption is much milder Actually, I have a hidden slide for that one as well.
I see. Because okay, because somebody was also pointing out that the roots cluster around plus and minus 1 for Legendre polynomials a little bit. Yeah. Okay.
Yeah, and so it's fine for us that they cluster a little bit. They just can't cluster too much. And so here's the actual assumption that we make. So if we write the roots like this, sort of between -1 and +1, and sort of look at their arc cosine and think of that as living on the unit circle, then we sort of require that in any reasonably big enough arc, there's about the right number of roots in each arc.
Okay.
And this is true for all of the families of orthogonal polynomials that we consider. In particular, it's true for Jacobi and also thus in particular for Legendre.
That sounds good. And then I think I see that Holger has a question here. Let me see if I can find him and allow him to speak so he can ask his question.
Okay.
It's going to challenge my ability to deal with alphabetical order. Okay, Holger, you should be able to talk now if you want to unmute yourself and ask your question.
Hi. So at some point you make an assumption on the entries of f that they should scale in magnitude like 1/√n. So that was on one of the slides.
Yes.
So I wonder whether that's true in general, because for the continuous orthogonal polynomials, this will not be true, like some scaling.
That's right. Yeah. So it is true for Jacobi polynomials. Actually, it's not obvious. We had to do a little bit more work to establish it, even for the discrete Jacobi transform. And you're right that it might not be true in general for orthogonal polynomial families. Actually, the more precise statement of our theorem, it has the assumption doesn't mean that it actually has to be less than 1/√n, but rather that there's that number, that maximum magnitude times that maximum magnitude squared times n shows up in the guarantees. So it does degrade gracefully if it's a little bit bigger than that, but you're absolutely right that there are probably some families for which this might not hold. Yeah.
Okay, thanks.
Yeah, great question.
I think that's it for the time being.
Awesome. Okay. Cool. How long is this talk supposed to be? I probably should have asked that before preparing the slides.
Yeah, usually like 50 minutes, but you know.
Sounds good. No, I don't want to keep anyone too long in the interest of reducing Zoom fatigue. Yeah. So that gives me 20 more minutes. Can I do math? Yeah. Okay.
Yeah, sounds good.
Okay.
We're generous, if you don't mind your time.
Okay, so I'll sort of give a high-level overview of how the proof goes. And for those of you who are familiar with the sparse Fourier transform, this is going to look pretty familiar. So let me start with, I guess, a quick overview of the sparse Fourier transform, because it's that framework that we're working into. And then I'll try to at least highlight some of the main issues that come up when generalizing it and how we get around them. So how does the sparse Fourier transform work? So here's a super high level idea. I encourage folks to take a look at this survey by Gilbert, Indyk, and Schmidt for more details. These really cool algorithms. But the basic idea is as follows. So suppose I have, now F is my Fourier matrix, the discrete Fourier transform. F times V is equal to some sparse vector Y. The first idea is I'm going to multiply this equation on both sides by some diagonal matrix, which I kind of think of as a filter. So this diagonal matrix is going to have a few entries which are pretty big, let's say pretty close to 1, and then a bunch of entries which are really small. And the hope is that by doing this, I'm going to isolate one of these k spikes in my vector y. So hopefully I'll end up with just one spike, and then all the rest will get multiplied by these really small values, and they'll kind of go away. And so this is sort of the idea behind reducing to the one sparse case. And then the hope is that if we let v prime be the inverse transform of this one sparse y prime, then we can somehow gain query access to this vector v prime using our ability to query v, and using that, use sort of a one sparse solver to figure out what y prime is. And then once we know what y prime is, we can basically subtract it off and recurse. So we have our original vector y, we can subtract off y prime. This is going to kill one of the spikes, and now I'm left with a k-1 sparse vector. And now I can recurse using query access to v minus v prime, assuming I can somehow get query access to v prime. So that's sort of the basic outline. There are a lot of issues that happen when generalizing this. So let me highlight 3 of them. 2 of them we deal with, and 1 of them I don't know how to deal with. So the first one, and this is sort of the main one, is how do we design this filter in order to give us access to v prime? So the way it works for the sparse Fourier transform typically is the following. So I'm just repeating some of these equations from the previous slide. So suppose that I've done this thing where I've multiplied by this filter to get this one sparse vector y prime. And now I'm going to suppose that v prime is the inverse transform of y prime and try to solve the one sparse problem. If we write down v prime in terms of v, it's going to look something like this. All right, so because v prime is f transpose times y prime, and y prime is equal to db times f times v. So v prime is equal to f transpose times db times f times v. And we want query access to v prime, but we have query access to v. So this will work out well as long as this product here, f transpose db f, is row sparse, meaning that there's not too many non-zeros in any row, or at least not too many big entries in any row. If that's the case, then we can simulate query access to v prime by using query access to v, because entry of v prime is just going to be some sparse linear combination of just a few entries of v. So for the sparse FFT, there's been tons of work on designing filters that are specific to the Fourier transform that do this. So in particular, this matrix is row sparse, and this filter db can sort of effectively isolate a spike. So the main challenge that we're facing in this work is we need to design a filter that works for all orthogonal polynomial transforms. And that's what we do. And I think that's probably the main sort of new conceptual contribution of this work, is coming up with such a filter. Okay, so that's the first issue in adapting this to general OPs. How do we get query access to this v prime? The second issue is sort of a more technical issue, which is that the black box sort of one sparse solver in the sparse FFT is not actually black box if you actually go and look at those works. So it's definitely often presented that way, and conceptually it certainly is like a separate black box thing. But in the actual implementations of how these algorithms work, things are sort of all mixed up in a way that really uses the structure of the Fourier transform. So there is still a little bit of work to be done, sort of formally disentangling these things and actually making something that's really just uses a one sparse solver as a black box. So that's another thing that we do. And we hope that there's some value in sort of formally disentangling this so that we can use it later then by just plugging in some one sparse solver. Okay, so that's sort of the second thing that needs to be done. And the third thing, which I don't know how to do, is to figure out how to permute the entries of the vector v. So what do I mean by that? So remember that I said that the way these things work is that I have a sparse vector y, and I sort of mask it with this filter, and I'm going to get a one sparse vector y prime. This worked nicely in this picture where the filter is just sort of this contiguous block and the entries of y are all spread out, but you could imagine it going wrong if, for example, all the sparsity of y happened to be concentrated in the place where the filter was 1 or close to 1. So what's done in the sparse Fourier transform, or the sparse FFT, is to basically insert some permutation matrix here between the transform and the vector y in order to turn y into something that looks more like this, so that we can, at least with high probability, isolate some spike. In order for that to work with the how do we query v prime thing that I had on the previous slide, remember before we wanted this matrix to be row sparse, and now that means that we want this matrix, when I throw in this permutation, to be row sparse. So in the case of the sparse FFT, there are permutations pi, so that pi sort of plays nice with the DFT matrix F. in particular, pi f is equal to f times d prime for some nice diagonal matrix d prime. So basically, if you sort of dilate on one side of the transform, this is going to scramble up the coordinates on the other side. So that's super nice and useful for the sparse FFT, but unfortunately, we don't know how to generalize this to general orthogonal polynomial transforms, at least with the filter that we've managed to come up with, which does work for general orthogonal polynomial transforms. So this is going to lead to that assumption that the support of x hat is kind of spread out. What we're going to be able to get is a filter that can do contiguous chunks, sort of, can be centered wherever you want, but it's always going to be contiguous. And we don't know how to do this permutation thing, so we're just going to deal with this issue by assumption, by assuming it away. So we're going to assume that x hat is spread out. And if you could come up with some sort of permutation that played nice with our filter and or with the orthogonal polynomial transform matrix, that would solve this problem. So that's a cool open question. Cool. Okay, so for the remaining 12 minutes in this talk, I'm going to talk a little bit about each of these parts. So first is the reduction to the one sparse case for general orthogonal polynomial transforms, and in particular how we deal with these issues that come up. And then part 2, I'll wave my hands real quick at how we actually solve the problem for Jacobi transforms for the one sparse case. Okay, so what is the algorithm? So part 1, reduction to the one sparse case. So like I said, the main thing here is to come up with a filter that works for any orthogonal polynomial family. So we're going to use filters that look like this. So we're going to define a boxcar polynomial B. This is a polynomial, hopefully pretty low degree, so that it looks like this. So if you have some point theta that you want to center the boxcar around, then within some interval of width gamma, or 2 gamma, I guess, of theta, when I take b of the cosine of x, it's going to be real close to 1 plus or minus epsilon. And I look substantially outside that interval, so outside of theta minus 2 gamma or plus 2 gamma, then b of cosine of x is going to be real close to 0, between plus or minus epsilon. And then there's going to be these sort of transition regions here where b can be doing whatever it wants. And the main useful thing here that plays nice with general orthogonal polynomial transforms is that, in fact, these things exist with reasonably low degree b. So here's a theorem. For any theta you like, for any gamma, there is an epsilon theta gamma boxcar polynomial of degree at most big O of 1 over gamma epsilon. And this is actually just a pretty easy consequence of Jackson's theorem in approximation theory. So it uses Chebyshev polynomials. So armed with this nice low degree polynomial filter, we can then sort of actually get query access to B for general OP transforms. And so how does this work? So suppose that D is the degree of this boxcar polynomial B. And suppose that I'm looking at indices I and J, which are further apart than D. So D is strictly less than the absolute value difference between I and J. Now let's consider this matrix here, F transpose DF, which, remember, the whole goal was to get this thing to be row sparse, because that will allow us to query V prime given query access to V. All right, so if we take a look at this matrix, we can take a look at the ijth entry of this matrix. So just writing out what this is, okay, so we get a big sum here. The ijth entry looks like this, and we note that this is the sum over L of these nice weights, WL, times some polynomial of degree I plus J plus D. And because of our assumption on D, we know that the degree I plus J plus D is not too big. It's less than or equal to 2n minus 1. And remember, the whole point of Gaussian quadrature, which I said at the beginning, is that if you have such a polynomial and you sum it up at these particular nodes weighted by the weights WL, this is exactly equal to the integral of that same product, except now with the weight function WL. But now I have a product of let's just say that I is bigger than j. So I have a product of, the inner product of pi with some polynomial pj times b. And pj times b has degree d plus j, which by our assumption is strictly less than I. So that means I can expand pj times b as a sum, or as a linear combination of orthogonal polynomials in this family of degree less than I. And so then by the orthogonality condition, all this is going to vanish and I get 0. So what that means is that as long as d is strictly less than I minus j, I'm going to get a 0 entry in the ij place in this matrix. Right. So said another way, that means that this matrix basically kind of looks like this. It just has sort of a band of non-zeros on the diagonal, and all the rows are d-sparse. So this is exactly what we wanted. Hooray. Cool. And so someone asked earlier about sort of where the various powers of k come from. Here's sort of one place where they come in. The degree of this polynomial d, if you go back to that Jackson's theorem that I had on the previous slide, is going to be 1 over gamma times epsilon, where gamma is the separation between the spikes. And that separation is something like n divided by k squared. So already here we're picking up a k squared. And I actually don't really know how to deal with that. So that's sort of one place that it seems kind of hard to get rid of that. Cool. Okay, so then so now we have our filter, and the next goal is to try to actually get an algorithm to use this filter to peel off one spike at a time. So the basic idea is as follows. So suppose we've already recovered some of the spikes in our vector v hat, and I've stored those spikes in some vector z hat that I'm recovering here. So then we're going to look at this residual vector r hat, which is v hat, the vector that we're trying to find, minus z hat, the vector that we've recovered so far, which I can write again as the spiky part plus the noise part minus what I've discovered so far. So maybe it looks something like this. Here are the spikes that I have not yet recovered. Here's some spike that I did recover and subtracted it off. So now it just contributes to the noise. Great. And now I'm going to choose a random center of the boxcar polynomial b. And if I get lucky, I'll isolate some spike. So let's say I do that and I get lucky, I isolate this spike. Then I'm going to use query access to v to simulate v prime, which is the inverse transform of this one spiky vector here. And remember, we can do that because f transpose df is row sparse. And then this other thing that we're subtracting off, this is all stuff that we know, and z hat is k-sparse anyway, so we can always compute this in time they go of k. Cool. So now I have query access to v prime, so I can use the one-sparse solver to recover h, the location of this spike, and a twiddle, which is an approximation of the magnitude of the spike with high probability. And then I'll just say, okay, let's add this spike to z hat and move on. So this is the basic outline. It doesn't actually work for a couple of reasons. Maybe in the interest of time, I'll just kind of highlight the reasons and wave my hands real fast at how you get around it. This is sort of, mostly finicky stuff. So one issue is, like, if the boxcar comes up empty like that, I don't isolate the spike, then the conditions of the one-sparse solver are not satisfied, so it might just say garbage. What do we do then? The basic idea to deal with this is that we can basically just test to see whether or not we've actually isolated a spike, and we can do that by estimating the L2 norm of this supposedly one sparse vector that we've got, and then just estimate that from samples. And then we can also estimate the value of the spike that we think that this one sparse solver has returned. And if everything checks out, then we'll say, okay, yeah, that's a legit spike, and otherwise we'll reject it. So we can get around that. That's still a problem because, okay, now we're not returning garbage, but we don't know what to return. Well, okay, that can be pretty easily resolved. If I didn't get a spike this time, just try again. So we're going to just do a loop and iterate a bunch of times until we do isolate a spike. And then there's finally one more problem, which is when do we know when to stop? Like it might be the case that there's one really big spike, which the one-sparse solver is going to get and sort of subtract off, but it doesn't subtract it off enough to sort of make it small relative to everything else that's going on. So maybe it finds it again and again and again. And how do we know when we've sort of found these spikes enough times that they kind of get small? And so eventually we're going to want to recover each of these spikes fairly accurately, so we need to know when to stop. And the solution to this is basically, again, just throw it in a giant for loop one more time and try a bunch of times. And if we keep going for long enough without ever recovering a new spike, we know that sort of each of the spikes must have gotten hammered down enough that they're accurate enough. And that's when we choose to stop. So that's the basic idea. I have some slides here that I'm skipping in the interest of time with more details on them, so please ask me later. But it follows the sort of the logic of the sparse FFT very closely. There's just some sort of finicky details to deal with, especially to deal with noise. Cool. Okay, so I have just 2 minutes to talk about the one-sparse problem. So maybe I'll say again the basic idea and some of the hiccups that come up. So what is the one-sparse problem? So the one-sparse problem is as follows. Once again, I have my matrix F times some vector V, and I have some one-sparse vector V hat. I can multiply both sides of this matrix of this equation by the transpose, and I see that V, the vector that I have query access to, is basically equal to a bunch of polynomial evaluations. So polynomial evaluations at some root lambda h that I'm trying to find, plus some noise. And so our problem formally is that suppose that V hat is this one-sparse vector where the noise in W hat is not too big. And our goal is the following. Given query access to this vector plus noise, so that is I get to choose what I want to go in this little black box here, and I can say, all right, give me the nth polynomial evaluated at lambda h, give me the jth polynomial evaluated at lambda h, and so on. Plus, and I'm going to get that value plus a little bit of noise. Our goal is to find h. And then once we found h, the one-sparse support, it's not too hard to actually find the value, the magnitude at that value. Cool. Okay, so this is our goal. We're given query access to, we can choose which polynomial we want. We're going to see it at some particular root, and we want to figure out what is that root. One convenient thing here will be, instead of thinking about the roots lambda h sort of between -1 and 1, it will be convenient to think about the r cosines of those roots, just like the picture I had before when talking about how spread out they have to be. So instead of thinking about lambda h being here on the real line between -1 and 1, let's think about theta h, which is the angle of this line here, so the r cosine of lambda h. In this language, our goal is, given query access to P of something of cos theta h plus some noise, we'd like to recover theta h. So I'm going to write that up here as the problem we want to solve. Okay, so at this point, I'm trying to solve this problem for Jacobi polynomials, and I have not yet defined Jacobi polynomials. So obviously we need to use the definition of Jacobi polynomials somewhere if we're going to solve this problem. So what are Jacobi polynomials? Okay, so they have many definitions. All of them are somewhat messy. This is just a screenshot of the Wikipedia page. So I'm actually not going to define Jacobi polynomials. Instead, I'm going to say a useful approximation that they satisfy, and this will be enough for us. So it is true, it is known that the Jacobi polynomial P sub j, evaluated at the cosine of some angle theta, has a form like this. It's equal to some stuff that we know, times the cosine of j times theta plus some other stuff that we know, plus or minus some small noise term. And here the stuff 1 and stuff 2, they depend on j and alpha and beta, and they also depend on theta in a mild way that's going to cancel out later. So I'm just going to ignore them for now. So the basic strategy that we follow is to say, first, okay, well, let's ignore all of this colored stuff that's going on. There's some stuff that I know about here. There's this little noise term. Let's ignore it. Let's just assume that P sub P sub j of cos theta is equal to cos j theta. This is actually just the same as the Chebyshev polynomial, if that were the case of the first kind. So the first thing we're going to do is actually just solve that problem. So given query access to cos of something times theta h plus or minus some small noise epsilon, we're going to recover a small list of possible h's. And once we solve that problem, we're going to use that to solve the more general problem for Jacobi polynomials. So we're going to use this approximation here to actually solve the problem that we're trying to solve. Okay, so I think I'm out of time, and I want to be mindful about Zoom's fatigue. So I'll just say that basically this is the strategy, and solving this problem here. Maybe I'll just do one quick graphic to give the intuition behind this. And then say there are some hiccups and we deal with it. But the basic idea is as follows. So there's this theta h that I want to find, and I'm giving query access to cosine of theta h times something plus or minus some noise. So here's theta h. And suppose I get cosine of theta h, that's down here, plus or minus some noise. So I get some small interval that cosine of theta h might live in. So then I know that theta h itself lives in this arc up here. Theta h is between 0 and pi. Okay, great. Now I can do the same thing for 2 times theta h. I know that the cosine lives down there, so the arc cosine is going to live in one of these two things. Okay, so now if I just sort of shrink everything back, what I get is that the original theta of h, it lives in the intersection of the purple thing and the pink thing. Well, that intersection is now much smaller. So I've sort of narrowed down the region where theta h can live by roughly a factor of 2. And so basically the idea is like, okay, I'll go back here. I'll say, all right, now I've narrowed it down. And then I'm going to repeat for 4 theta, 8 theta, 16 theta, 2 to the t theta, and so on. So again, if you're familiar with sparse Fourier, the sparse SFFT, this is very similar to the one-sparse solver used there. There's a few hiccups that show up. So for example, one hiccup might be if I happen to have 2 to the j theta land here, then this does not really help me narrow anything down because this arc is so big. Another hiccup happens with the sign ambiguity of the arc cosine. If I end up with like both of these regions living inside the purple region, it also doesn't help me narrow it down. Basically, the way to deal with both of these hiccups is just to fiddle with this value of 2 to the j until it works out. That's the basic idea. Okay, so that solves this first problem. All right, now I'm over time, so I'm going to stop. So now there's a bunch of approximation stuff that needs to be done in order to not forget about all this colored stuff and actually put it back in. But once we do that, that's sort of the basic idea for the one-sparse solver. Okay, so quick recap. We have this reduction from one-sparse to k-sparse, which works for any orthogonal polynomial family. Then we gave a one-sparse solver for the Jacobi polynomials, or for the Jacobi transform. And together, these give the first sublinear-time algorithms with provable guarantees for approximately sparse recovery for discrete Jacobi transforms, at least under some assumptions, which makes us happy. So just a few quick open questions. I think I've already mentioned several, but maybe I'll just highlight some that I've already said. We'd really like to improve this dependence on k from k to the 8 to something better. Also, someone asked about the dependence on delta. That's also something that could be improved. And then also removing these assumptions about having well-separated support and handling more noise. And I think both of those assumptions might be able to be removed if you could come up with some nice permutation that kind of plays nice with orthogonal polynomial transforms. Okay, so with that, sorry for going over. I will stop and take any more questions you have. Thanks.
Thanks, Mary. So if the participants have any more questions, this is a good time to put them in the Q&A. Otherwise, if the panelists have any questions, please feel free to unmute yourself and ask.
So Mary, did you make the graduate student involved implement this and try it out on some Jacobi polynomials?
I don't treat graduate students that way, Mark. I don't know what you do. But no, it's a really good question. We have not implemented this. And yeah, I think this is something where we're thinking about doing, is like, how do we actually make this practical? Right now, the k to the 8 and all those other things are sort of getting in between this and being practical, but I really hope that this is sort of the first in a line of work that will actually lead to something that we could actually implement.
Sometimes you find that the implementation, the k to the 8, isn't really k to the 8, and it sort of works squared or k, and sometimes you find the other way, and but yeah. What's the graduate student's first name?
Albert Gu is the PhD student on this paper, and he's great.
You can't be proud of your thesis until you implement this thing. It's got to be in there, man. Just letting you know.
Actually, to be fair, Albert might have implemented it. I don't know. So I'm not going to say for certain that he hasn't. It's not in the paper.
So we have one question from the audience related to Mark's questions. Are there applications in mind which an implementation might be useful for?
That's a really good question. Yeah, so our motivation was more from just like trying to generalize from the sparse FFT, and we were kind of hoping that applications would come along. We didn't have any particular application in mind when we started, although yeah, we're sort of exploring some now.
Great. Okay, other questions?